Okay, so we have been using the antiderivative to find the integral of a function. That's how you do it. But we've been having to use trial and error to do that, and that's what you have to do. But there are certain patterns that emerge that help you to be able to deal with more complicated indefinite integrals by knowing just a few rules that tell you how these things act. So for example, when you're finding the integral of 5x to the fourth dx, you have to think in your mind, okay, what function has the derivative 5x to the fourth, and then go backwards and just figure it out, and that's x to the fifth. And then you add c because you're saying, well, it's x to the fifth, but it could have some constant added to it, and it would still have the same derivative, 5x to the fourth. So that's why we put the c there, just to say it could be any function that looks like this, x to the fifth plus some constant. All right. Now what we're going to do is just look at some generalizations about indefinite integrals for certain kinds of functions that'll kind of help you simplify the process. Now that one we just did wasn't hard, but when they start getting more complicated, it's harder and harder to figure out, by trial and error, what the thing is that has that derivative. All right, so the integral of a constant, first of all, that's pretty simple, but it's a good thing to start with just to generalize. Whenever you have the integral of a constant, just a number like 5, that, it's pretty easy to remember that, for example, the integral of 5x dx is 5x plus c, because the derivative of 5x is 5. All right, so whenever you take the integral of a constant, it's just going to be that number, that constant, times x or t or u or whatever that variable of integration is. And that always is right here. It always tells you what that letter is. So the derivative, or the integral of 5 dx is 5x plus c. The integral of 5 dt would be 5t plus c. The integral of 5 du would be 5u plus c, etc. So basically, we're getting to this point where we can generalize, and this is pretty obvious, of course, that the integral of any constant dx is equal to kx plus c. So that's the integral of a constant. That's the basic general rule. And that's very obvious, but we are going to kind of use that to make a couple of other rules that will help some other integrals be a little bit easier. Okay, so the integral of a constant times a function is going to look something like this, where you have the integral of, some constant, like 4, times some function, like x squared. And when you're doing that integral, it's not quite as simple, because you have to go back and think, okay, what has that as its derivative? And it's a little more complicated. It's going to be something x cubed, but it's going to be some fraction, and it's not as easy as it could be. All right, so there are some rules properties of this kind of integral that makes it a little more easy. So let's just see what's going on. This is, again, it's something that's going to keep us from having to use trial and error all the time. So it'll be kind of a formula. So first of all, we already know that the derivative of a constant times a function is equal to the constant times the derivative of the function. All right, and of course that sounds a lot more complicated than it actually is, but so when you take the derivative of something like 4x squared, you know that that's 8x, because you multiply the exponent times the constant, and then you subtract 1 from the exponent. All right, well, if you think about it, that is the same thing as 4 times the derivative of x squared, because the derivative of x squared is 2x. So 4 times 2x, which is 8x. All right, So when you take the derivative, not the integral, but when you take the, well, it will be the integral, but in a second I'm going to show you that it works for that too. So whenever you take the derivative of a constant times a function, you can just put the constant out in front of the integral. You can move the constant over that operator. And that only works if it's a constant. And it'll always work. So actually, it turns out that that also works for an integral. So if you can factor out some constant that makes the integral easier, you can move that constant to the left of the integral sign. So I'm going to show you how that works. Okay, so for example, here's an easy integral that we know already, the integral of 2x dx. Okay, we know that the antiderivative of 2x is x squared, so we know that's x squared plus c. That one's easy. But what if we have the integral of 8x dx? That's not quite as easy because we have to figure out, okay, it's going to be x squared, and then, I mean, it's not hard, but still, it takes a little more thought. So if it was even more complicated, you can see that we would like to have some kind of rule. All right, so the derivative of 8x dx, I could rewrite it so that it looks more like this up here. I could say, all right, well, I could say that is 4 times 2x dx. And I know 2x dx has the integral x squared. So actually, kind of, it kind of follows from what we did with the derivative that I can actually move that 4 to the left of the integral sign. Because really the integration is just the inverse operation of d dx, of the derivative. And so it's just like multiplication and division. It's like factoring out things. You can do it with either operation. So we could do a long proof about that, or, you know, explain it more, but I'm just going to tell you that you can move the 4 outside the integral. So this is 4 times the integral of 2x dx, and we know that the integral of 2x dx is x squared. So we would have 4 times x squared plus c, because the integral of 2x dx is actually x squared plus c, because you have to say it's anything that looks like that, plus maybe some constant. And when you distribute the 4, you got 4x squared plus 4c, but c is just any possible constant. And you can write any possible constant from 4c the same way. So you don't need to put that 4 in front of the c, because it just, that variable there just represents any possible constant. And so it can still be called c. All right, so what you find out is that you have this rule that whenever you take the integral of a constant times a function, you can put the constant to the left of the integral sign. You can move it outside and just multiply it by that derivative. And so hopefully you can move a constant outside to give you an easier derivative to find. All right, because here, I mean, I could have moved the 8 outside, but it was easier to move the 4 outside and end up with 2x, because I know the integral of 2x is x squared, and it's just an easy one to find. So as you have more experience, you'll figure out, okay, what do I need to factor out to give me the easiest possible integral? Okay, so the only thing you have to be careful about is never move a variable outside the integral sign. Just constants can move. All right, so if you have something like this, the integral of 4 cosine t dt, you can move that 4 outside the integral sign, and you'll just have the integral of cosine t dt, which is an easy one because we know that the derivative of sine is cosine, so the antiderivative of cosine is sine. So that's just 4 sine t plus c. Now here on this next example, we've got the integral of sine u du. The antiderivative of negative sine is cosine, because cosine, the derivative of cosine is negative sine. So this is not negative sine, and so it just makes it a little more complicated. It's not that bad, but just a trick you could do would be to change this to the integral of negative 1 times negative 1 times sine u du. Why would I do that? Well, if I do that, I can move the one of those negative ones outside the integral. And then the other one is left inside, and it'll be negative sine u du. And since the antiderivative of negative sine is cosine, it just makes it easier to say, okay, well, that's negative from this one, cosine u plus c. So that's just a little trick. Sometimes you might want to change the sign on something, and that allows you to do that if you can just multiply it by -1 times -1, which is just 1, which means you're not changing anything, and then you move one of those outside and the other one stays inside, and it sometimes might make it easier, especially on a problem like that where you know the antiderivative of negative sign is cosine, and it just makes it an easier integral. All right. So we're going to move on to the integral of x to the n. Okay, so the integral of x to the n. We know the derivative of something like x to the fourth is 4x cubed. Okay, so that's pretty easy. If we took the integral of 4x cubed, we'd get x to the fourth because that's the antiderivative. So what we're going to do is we're going to think exactly what is happening when we transform 4x cubed into x to the fourth. So in other words, when I'm taking the integral of something like 4x cubed and I get x to the fourth, 4x cubed dx, and I get x to the fourth plus c, let's think about exactly algebraically what's happening when you transform 4x cubed into x to the fourth, so that if I have something more complicated than 4x cubed, I can do the same thing to it. All right, so if you're transforming 4x cubed into x to the fourth, what are you doing? Well, you're adding 1 to the exponent, and then you're dividing by 4. So you have 4x cubed. If you want to turn that into x to the fourth, first of all, you're going to add 1 to the exponent, and you're going to divide by 4, which is 3 plus 1. All right, it's the exponent that we did have at plus 1, and then that will give us x to the fourth. So algebraically, that's what's happening whenever you have a constant times, or whenever you have an x to a power. All right, if you're taking the integral of x to a power, in general, what you're doing is you are adding 1 to the exponent. So if you have the integral of x to the n, you add 1 to the exponent, and then you divide by that exponent that you started with plus 1. So that's what happens, and so we have this rule that we can use whenever we have that form of an integral, where we have the integral of x to the n. We just don't have to sit there and do trial and error. We can remember that basically what happens is you add 1 to the exponent, and then you divide by the exponent plus 1, the exponent you started with plus 1. Okay, so let's look at some examples. So this first one, I've got the integral of 5s to the negative 20 ds. So I'm just going to use that rule. I'm going to take 5s to the negative 20. I'm going to add 1 to the exponent. So that'll give me negative 19. And then I'm going to divide by the exponent plus 1, which is also negative 19. So, and then plus c. So that's what that integral is. And that would have been, a little more complicated to try to think about without that rule. All right, over here I've got the integral, it should be dt here. The integral of 1/3 times the cube root of t squared. All right, well, that's looking really complicated, but first of all, I can take the 1/3 outside the integral because it's a constant. And then I can change this to a fractional exponent, t to the 2/3 dt. And now I can use that rule about x to the n, taking the integral of x to the n. So 1/3 times, I'm going to add 1 to the exponent, so 2/3 plus 3/3 is 5/3. And then I'm going to divide by the exponent plus 1, which is also 5/3. And so when I multiply this out, well, that should be plus c. And then when I multiply this out, I'm going to get 1/5 t to the 5/3 plus c. All right, so we got the next one over here. We've got the integral of 3 du over the square root of u. All right, first of all, I can put the 3 on the outside of the integral. And then 1 over the square root of u is just u to the negative 1/2. And then you've got your du. So I'm going to do the exact same rule. 3 times, I'm going to add 1 to the exponent, so that's going to give me u to the 1/2. And I'm going to divide by the exponent plus 1, which is also 1/2, and plus c. So that's going to be 6 u to the 1/2 plus c, or you could write it 6 square root of u plus c. All right, and then I have this last one, 5z to the pi dz. Looks really complicated, but it's not. You just move the 5 outside the integral, and then you've got z to the pi dz, and then you just add 1 to the exponent, pi plus 1, and then divide by the exponent plus 1, which is also pi plus 1, and then plus c, and then you could just rewrite that as, I mean, it's never going to look good no matter what you do, so just 5z to the pi plus 1 over pi plus 1 plus c.